Benvenuti a tutti. Tanto i sottotitoli che stanno comparendo saranno assurdi perché sono settati sull'inglese, quindi non guardateli. Abbiamo come ospite, come primo ospite questo pomeriggio Marco Lovati, che quando ci siamo sentiti stava alla Dall'Arma University e ora invece ci sta parlando dalla Cina, quindi ha fatto un piccolo spostamento e poi mi ha detto che si sposterà ancora, andrà a Helsinki, stavamo parlando poco fa prima del collegamento, quindi è una di quelle menti, quei cervelli in fuga che sono andati via dall'Italia e ci siamo persi, ma noi cerchiamo di tenerceli vicini anche con questo tipo di attività, di eventi. Ha un curriculum ovviamente ampio, ha fatto un sacco di cose, adesso non sto a raccontarvelo nel dettaglio. Fondamentalmente lavora su modelli di business per sistemi fotovoltaici condivisi, quindi è un tema che ci interessa particolarmente. Quindi adesso non so esattamente su che dettaglio vorrà approfondire, però insomma il titolo Local Energy Communities ci fa immaginare il tema, che poi è quello che abbiamo toccato variamente nei contributi precedenti, cioè il fatto che dobbiamo costruire comunità, e quindi che l'energia, la gestione energetica della città e la costruzione di smart city passa per la costruzione di comunità attraverso le opportune tecnologie. Quindi la tecnologia da sola non serve, ma costruiamo comunità energetica in questo caso, e quindi la tecnologia sicuramente aiuta moltissimo, ma pur sempre parliamo di comunità. I sottotitoli sono in italiano perché l'intervento sarà in inglese, o come sempre su chat potete interagire o anche intervenire se ci fosse la necessità per fare domande e avere un'interazione diretta con il nostro relatore. Quindi lascio la parola a dottor Lovati, grazie.
Una brevissima precisazione, ovviamente se qualcuno farà domande in italiano posso benissimo rispondere in italiano. La presentazione era in inglese per comodità, diciamo, perché tutti i paper sono in inglese, eccetera. Comunque, the presentation is about local energy communities and more precisely effective system and market design. So we will see the design of the photovoltaic system and the design of the market for an economically sustainable photovoltaic future. Next slide, please. So my name is Marco Lovati, and you can find information about me on ResearchGate, which is my main social network, by scanning the QR code or by going on the link below. Next. So we see recently that many people are protesting for the climate because we have the perception that who is in power and in general our society is not doing enough. And one thing that saddens me a little bit is that usually we see that the economy and the environment are often seen as enemies, so as something opposed to each other. So it's like jobs against the planet, or we see banks against the planet, etc. And often these protests end up with a call to action from politicians. Next. But if we see, for example, the signing of the Paris Agreement, we see that the vast majority of countries, and for sure the vast majority of the global wealth, of the global GDP, already ratified the Paris Agreement. So there is a political will to change the situation. Next. But what if it's only a piece of paper? I mean, what if the Paris Agreement will not really change the situation, but is only a signature on a piece of paper. Sometimes I fear that this is the case. Next slide, please. So we do call to action from politicians, but here in this slide, in a provocatory way, you can see a politician confronted with a problem that is much smaller in scale compared to the global warming. Guess what he can do to fix this problem? The point is that the politicians cannot fix the problem because the politicians do not create value, they just transfer value. So we need the cooperation of the whole society to solve the problem of the environment, the global warming. Thank you, great. It was correct. Next slide, thank you. So basically, you can have many ways to compel the people to cooperate, but they fall into large category. You can punish those who don't cooperate, or you can reward those who do cooperate. Next slide. And here I give you a secret tip. No, yeah, it was two slides similar, but yeah, never mind. The secret tip is like you have these two strategy, like either punish those who don't cooperate or reward those who cooperate. But one of these two is really dangerous because it can create a social problem, like a social upheaval. So the economy and the environment are really enemies. Next slide. If we believe that we should punish those who do not cooperate, of course, yes. But if we believe that we want to reward the people who indeed do something for the planet, we understand that it's not like this. So the economy and the environment are not enemies, but that we should design an economic system that it's made in a way that it's rewarding to improve the situation of the environment. So it is up to us. Next slide. And there is a very simple example that we can do. This is like a toy example because it's very simplified. But we can see, for example, that we can have carbon tax where all the industries in a specific branch, here I choose the beer breweries, when they have high CO2 emission, they have to pay taxes, so they are punished. Or we can simply have a carbon trading system where it's true that they pay taxes, but the taxes don't go for other reasons, but they are simply given back in the form of incentives to those breweries that indeed are consuming less. So the people don't have necessarily to give money to a government, but they can simply buy some sort of carbon credit from other more virtuous institutions. Next. So this was just a simple example to show that there are a lot of things that we can do that do not necessarily harm the economy. And now we go on the topic of this workshop, which is photovoltaics, and more specifically, building or urban photovoltaics. So not freestanding photovoltaic that sell all the electricity to the grid, but photovoltaics that are integrated in buildings and have as a main business model the self-consumption, so to consume your own electricity. Next slide. So a few years ago, when I started my PhD in our company, we noticed that there is a problem in the way to design a photovoltaic system. Here you can see the typical architectural workflow that goes from an earlier design stage to a later design stage, and then there is an iteration. So you have a design idea, you try to design it, you evaluate, and if it's not satisfactory, you go back to the drawing board and you put all the constraints that you have, like the need for windows, the need for the structure to resist, etc. So you can see that we would like to have the PV constraints alongside all the other functions of the building, while unfortunately in our practice, we always had it later. Next slide. So we decided to create an algorithm, an optimization algorithm that given a weather file, so for example, an Energy Plus EPW weather file, and the geometry of the building can create the irradiation, and then the irradiation together with the hourly electric demand of the building, together with a series of techno-economic inputs such as the cost of the PV system, the cost of the battery, etc., they all together go in an optimization algorithm that suggests you what is the correct PV capacity, what is the correct battery capacity, so the storage, and also the positions of the PV system. Next slide. So this works with OBJ geometry. We are trying now to use IFC, so it will be possible to input Revit files into the tool and also exports OBJ. Next slide. So here we can see a little bit higher level of detail on how the tool is working. Basically, we have the context geometry and the measuring geometry, which is like the shape of the building and all the areas where PV can be installed. And the irradiation over the geometry of the building is calculated with the ray tracing. So you can see it's a little bit detailed, so I will not go on. So next slide. Of course, if somebody has a question, but to really simplify it, it basically works like a painting. So this is the same algorithm, just we ask the algorithm to copy the picture of a horse, and the algorithm had some strokes of color. So it could stroke some disc with different dimension, different position, and different color. And one by one, he decided to put one stroke of color at a time until the white canvas was becoming similar to the picture of a horse, basically. Next slide. So then the same thing can be done on a building. So you can basically paint the photovoltaic system on the facade of a building. Here we can see quickly an example. This was a project for a school in northern Italy. And you can see that there are two large surfaces available for PV. One is on the roof and one is on the facade. Next slide, please. So you can see basically that on an annual basis, the roof gets more energy. You can see that April, May till August, basically the roof gets much more energy than the facade. But we can also see that the facade can take a little bit more energy in the winter month. And if we see the electric demand, because this school was equipped with a heat pump system, we can see that the electric demand is a bit higher during the winter month because of the need for heating. Next slide, please. So what we did, we launched the optimization system and we try it with electric storage and without electric storage. And we can see the following thing, that if we calculate the net present value, which is basically the value of the investment, it's a number that if it's positive, it means that you have to invest the money. If it's negative, not, of course. We see that this has a maximum. So if we look on the x-axis in either of these two charts, there is the capacity. And on the y-axis, there is the net present value. We can see that if you install around 60 kilowatt peak of PV, you likely have the best net present value. Then you can see a gray band around because the software has some stochastic element. So for example, the degradation of the PV, so how much it becomes older, how fast it becomes older. So the changing of the demand, the changing of the prices over time, these are all things that we do not know. So of course, if you are optimistic, so if you think that everything will go in favor of PV, you should install more than 70 kilowatt peak. If you are pessimistic, you can install around 50. But you can see that if you install 60, which is the expected value, in either of the other cases, you're still very close to the maximum. So it's really the safe bet. The MP, medium point, there is low point, high point, medium point. That one is actually very robust in terms of optimization of the capacity. But the capacity is not all. Next slide. Because also the position are important. If you can see these 3 points, pessimistic, medium, and optimistic, you can see that in all of them, part of the system is installed on the facade. So despite having a lower irradiation overall, it is installed on the facade because it has a better matching of the electric demand and production. So even though there is still potential on the roof, you can see the bar on the right, the algorithm stops to paint PV on the roof and start to paint it on the facade. Next slide. Then we tried to force the algorithm to use all the roof first, and we see that it installs overall less PV. So if we allow it to put part of the system on the facade, we see that it installs slightly more PV than only on the roof. Next slide. And then we can see that it's not guaranteed that the net present value will increase when we put part of the system on the facade, but is at least more likely. So if you see the x-axis, you will see that the gain is very low. But the surprising thing is that there is gain at all, because if you ask to most of the PV experts, nobody ever will suggest you to put part of the system on the facade, but sometimes they might be wrong. I mean, at least if you don't have a gain, a real gain, because it's a very small gain, at least you have the freedom to put part of the system on the facade, which is interesting, at least for the look of the building, at least. But even more important, you can substitute some cladding material with PV and so on. Next slide. So if you want to see this study, you can go on Science Direct on the link or scan the QR code. Next. So if PV in self-consumption is already profitable, why do we need energy communities? If somebody is skeptical, will think so. So of course, a well-designed, a well-sized PV system is profitable with today prices of PV and electricity. But the problem is that most of the cost is upfront. So in the beginning of the investment, you have to pay a lot, and then the maintenance is very cheap. So to change a couple of modules or to change the inverter over 30 years, or to clean every year or every couple of years the modules is not really much expensive. The biggest expense is the beginning. So this means that even though you have an interesting internal rate of return, the payback time is quite long. Furthermore, the aggregation has many benefits, and we can see why in a quantitative way. Next slide, please. So here was a very theoretical study. It was not a real case study, but here we had 16 households which were located in London. The electric demand is real, so these are real people. And you can see that they are characterized with this B, C, D. This is basically the social status. It came from an online database, which was classified by Acorn classification system. And then you can see on the right the same 16 houses. This is really a simplified model, completely theoretical model. But you can see the irradiation over the different slopes of the roof in this system. Next slide, please. So we try to optimize first every house individually, and then we tried to aggregate the houses, so to make microgrids. And we see, as you can see, if you want to get the optimal net present value, you can see that the single houses, their average capacity is half a kilowatt per house, the optimal one. The quarters, so 4 houses in every quarter, it's a little bit higher. And if you make a microgrid with all 16 together, it's still a little bit better. So basically the aggregation favors a higher integration of PV system, very high, more than 100% more. Next slide, please. And here you can see from the top, of course, if you optimize each house singularly, each of them will install 1 or 2 modules. Then if you use the quarters, already you have a gain, because in this case in London, it doesn't pay to use the east and west facade due to the demand shape and due to the irradiation, which is quite low. So you don't have problems of overconsumption. You only want to maximize the irradiation. So if you let the algorithm use the microgrid, you will see that the algorithm will use only the south slopes. And even so, there is still a gain aggregating all 16 the houses. So it installs a little bit more. You can see it from the picture. Next slide, please. So here we see that the self-consumption and the self-sufficiency are both improving. The self-consumption is basically how much of your energy is consumed on site. The self-sufficiency is how much of your demand you can cover. So you can see that when you optimize the houses singularly, you have a self-sufficiency below 15% and a self-consumption below 90%. Then when you aggregate the houses, you can see that the self-consumption improves and the self-sufficiency also improves. So you have a gain on 2 opposing metrics. So it's very profitable. Next slide. So here we see the levelized cost of electricity of a different case. So here we are not trying to have the best net present value, but here we are trying to cover 27% of the electric demand, which was the 2030 agreement in 2017. So now it's 32%. They became a little bit more ambitious. So basically this paper is outdated, but at the time it was 27%. So we said, how much do you have to pay if you want to cover 27% all with PV? And you can see that also in this case, of course, you have to install a little bit of electric storage. You cannot reach 27% only with PV, but you can see that if you aggregate the complete block, the storage almost fall to 0. So it's like it's really minimum. While in general, the average of the house still is very low. It's 400 watt-hour per house. And it increased a little bit when you aggregate the 4 quarters. But if you see the LCOE, so the levelized cost of electricity, you see that thanks to aggregation, the levelized cost of electricity is falling. The chart on the right, you can see that the single houses, it's between 15 and 16 cents. Then it goes down to 14, and then it goes even lower to 13, because by aggregating more and more, you use only the best part of the wall surface. You are not forced to put modules where there is not so much irradiation. And even more, the self-consumed LCOE. So it's not the LCOE of all the electricity that you produce, because parts goes to the grid, is the LCOE of the electricity that you contemporaneously produce and consume. So you can see it's a little bit higher, of course, because part of the electricity that you produce is lost. But you can see that there is a very large gain, especially when you do the aggregation of the first 4 houses. Next slide, please. And also this study, it can be found on ResearchGate, because it was a conference paper, and you can, it's very long, the link, but if you have the slide, you can just scan the QR code and you can go look it up. Next slide. So finally, we saw that the energy communities are very important. And so we can finally start to study them. And to study them, we decide to use agent-based modeling. So we don't use a control algorithm. So we don't have a big brain that from above direct everything, but we prefer to have agents that are all stupid, but they are numerous. And so from their interaction, there is the behavior of the system. So you can divide these energy communities in 3 families, basically. You can see on the drawing on the left. So the first one, the most simple, is the local energy provider. So you have a microgrid, then you have one household or one third-party institution that is responsible for providing electricity to the other. So they own the infrastructure and sell the electricity. And this is called local energy providers, because these are providers. Then there is the case B, which is the local energy community. So it's like all the households together are shareholder of a common infrastructure, and this common infrastructure is shared. And last but not least, in fact, it is the most important. It is so important that the other 2 categories are only special case of this one, is the local energy market. So there are no rules. Everything is valid. Everybody can own parts of PV or storage or nothing. Everything is perfect. So this is personally my favorite, because in reality it's more easy to have a free market, because maybe somebody doesn't want to pay for PV, or maybe somebody wants to pay more and invest more because they think they can have some economic gain, or because they are rich and they want to be green. Whatever the reason, it's very likely that you can build a microgrid and then don't have any agreement between the people inside. We can also create a map of the behavior of a microgrid, which is the one on the right. So there are 3 dimensions. One is controlled versus emergent. Where you have controlled, it's like the big brain from above. Emergent, it emerges from the interaction of the stupid, let's say the dumb agents. Then you have centralized against decentralized. So in the centralized is like one agent has the infrastructure. So you have the case of the local energy providers. In the decentralized, it can be either the community or the market. What is the difference between these 2? If it's collective or individual. So if it's collective, it's a community. So there is a big institution where many households are part of it. If it's individual, it's completely free, which is the pink corner in this behavior map that we see. Next slide. So we see that we started to experiment with these microgrids and with the interaction of the agents inside. We have a cluster of 48 households. This cluster is located in Sunnanjo, is the name. It's It's a small fraction of the municipality of Ludvika in Dalarna in Sweden. And this small community is now undergoing energy retrofit. So they are installing a microgrid PV system on the roof and on the facade, and also a new heat pump, which in this study we didn't consider the consumption of the heat pump because we only wanted to focus on the households, and the heat pump basically would be the same for everybody because it's a centralized load. So it was not so interesting and we ignored, but it will be there. Next slide, please. So here you can see the model that we use, the simplified model that we use to calculate the irradiation over the surface. And then on the picture B, you can see all the areas that were made available for the PV. And in the table below, you can see basically how the optimization algorithm decided to put the PV system. So you will have most of the PV system, so almost 30 kilowatt, will be on the south slope, so in the central building, let's say. Then you will have a little bit of capacity on the east and west slopes of the roof, and also a little bit, it's really a minor quantity, but there is a little bit on the facade, on the south facade that you can see. Actually, it's the facade of it's part of the facade of the smallest, of the shortest building, because it has less shadow from the tree in the south. Next slide. So first of all, we plotted the self-sufficiency, and we can see that there is a huge difference between those who have a very high self-sufficiency and those who have a low self-sufficiency. Basically, the highest self-sufficiency have double of the other. And you can see the 50 percentile, it's between 18 and 20% of self-sufficiency. So still very high compared to the typical solar fraction of a country, for instance. Next slide. And you can see here, here we plotted the typical day, so the average day of the two extreme household. And we can see that the most self-sufficient, so the one that can cover most of its demand with PV, clearly has the use of heating at home. You can see that there is a spike of energy use around 12:30. So it means that very often they cook and eat meals at home at lunch, and not so often at dinner, perhaps because they don't cook so much for dinner. Maybe they have a small dinner, etc. While the other household, the lowest self-sufficiency, they basically never eat at home at lunch, but they always eat at home for breakfast and at dinner. You can see there is a very large spike around 8 p.m. in the evening. Next slide. And then we devised a formula to understand what is the impact of having high or low demand in a specific hour of the day. So we only focus on the green part of the chart, which means positive impact. So we took all the households that have a self-sufficiency above average, and we see which characteristic they have, and we see that they have a strong reduced consumption around 7-8 p.m. That's a very strong spike in negative. So they are well below the average in those areas. And of course, this is trivial. They are well above average during the hours of the day. You can see, this is quite interesting, that they are above the average all day long, but at 12, they are not so much above the average as they are, for instance, at 10 a.m. or at 2 p.m. Why this is so? Because at 12, many people, although not everybody, are eating at home. And so there is a very high spike in demand. And the photovoltaic system cannot keep up with the demand. So if you happen to have a very high consumption around 12:30, because it's the halfway of the time step, then you are not so much self-sufficient, because you most of the time you still need energy from the grid, just because everybody is consuming a lot. So it's not only there is sun, but the ideal is to consume a lot when there is sun and when the other people are not consuming. So you can see that there are two peaks at 10 a.m. and 2 p.m. Next slide, please. Then we can see something that was a little bit depressing, was a little bit a turn off as a result, because we see that the self-sufficiency is not that much important, but the most important thing is how much you consume overall. So you can see that there is a household that has an outlier high electricity demand, almost 12 megawatt hour. You are wondering why. Actually, these households are simulated with a software. I will show it later. In this case, there were the possibility to put grow lights, so to grow vegetables indoor. So probably this household had that, so that they were growing vegetables indoor with artificial light. And that's why they have such a high, outlier high electricity demand. But you can see basically that it's almost a linear correlation. So the more your cumulative demand, the more the energy you get from the PV. And this is sadly because even though the self-sufficiency can be 14 or 28%, so one double than the other, as you can see, the electric demand can be 2 megawatt hour or 8 megawatt hour. So it can be 4 times as high. So basically the self-sufficiency only becomes a noise in the capacity to use electricity from the PV system. And this could be corrected. So we can, for example, put the rule that the households that consume the least electricity are prioritized, so they get priority over the local electricity. Next slide, please. So we can see first of all a case of the local energy community where the electricity is given for free. What it means, of course, is not free. If there is a community, it means that everybody buy a share of the PV system. So we build the optimal PV system, but each single household pay a little bit in the beginning. And then every year, of course, there are costs for the maintenance, for changing the inverter, etc. But of course, when there is electricity, the electricity is free. So if the electricity is more than the electric demand, in that hour you pay zero. It's completely free for you because you are a shareholder of the community. Of course, if the demand of the community is too high, we have to buy a little bit of electricity from the grid, and so we pay for that much. So for example, if we can cover 80% of our demand and the other 20% we have to pay, we only pay 20% of the price of the electricity that we buy. And you can see that there is a noticeable advantage. You can see the price outside the microgrid, which is a typical residential pricing for Sweden. So it's like a little bit more than 16 cents during the winter, and around 12 cents of euro during the summer. You can see that inside the microgrid, the price is much lower. So there is, of course, a large advantage. There is free energy for all in many hours of the year, and at least in part in many other hours. Next slide, please. But there is a strong downside. As we saw before, the people who do not consume much, they use very little energy from the system. And on the other side, the people who consume a lot, they also are very effective in using the electricity from the shared PV system. So here we divided all the 48 households in the community in small, medium, and large consumer. And we see, unfortunately, that all, so 100% of the small consumers are losing money. So the balance, considering what they paid in the beginning and what they pay in maintenance, it's not enough. So they basically lose money over the lifetime of the system. While the large consumer invariably always gain money. So it's very good if you are among the large consumers in this small community, but otherwise it's not so pleasing to be part of this energy community, let's say. Next slide. Then we saw that if you give out the electricity at levelized cost of electricity, the share of costs and revenues are slightly more balanced. So you can see that, of course, now the medium consumers are almost all in the positive, and also the small consumer, although they still lose money, they lose a very, very minor amount, like they lose less than 10,000 kilo coronas, Swedish coronas, which is like less than 1,000 euro in 30 years, actually less than 500 euros in 30 years. So it becomes a little bit more manageable. This is a case in which the electricity that you buy from the community is not free, but is given at levelized cost of electricity, which is less than 10 cents per kilowatt hour. Next slide, please. And then we see the local energy provider. So here we imagine that the local energy provider can give different prices. And we created this N variable. So N0 is the levelized cost of the electricity. So it's the bottom, the lowest possible price that you can set. And N100 is the price of the grid. So 1.8 corona in the winter and 1.2 in the summer. So you can see that if you sell the electricity at your levelized cost of electricity, the internal rate of return is negative. And this, at first, I thought it was a bug, because I said, how is it possible? If I sell at my levelized cost of electricity, it should be 0. But the point is that your self-consumption is not 1. So all the electricity that you produce is not completely, perfectly consumed inside the microgrid, but part of it goes outside. And when it goes outside, it gets paid much less, because it's paid by the grid authority and not by your friends, like your peers' households. So in this case, you sell part of your energy at levelized cost of electricity, so without a profit, and the other part at a lower price, so you have losses. Then if you set, this is a strange number, but in fact is only made to balance out, to make everything even. So there is no benefit. You have an internal rate of return of 0. But basically, this price is very interesting, because it's the price at which nobody is losing money. Also, the small, if you can find this 9.43, let's say, also the small consumers, they will have no losses, because basically the price that you sell is high enough that you can compensate for the fact that you don't have a self-consumption of 1. And then you see increasingly higher and higher prices. The 9.43 is also interesting because it means that you didn't pay anything for your system. So you pay, but over the lifetime of the system completely pay itself out. So actually, if the local energy provider is the homeowner, for example, if it's a public entity, they could make a business model in which they use the photovoltaic material as a building material. So they don't earn anything from the sale of the energy, but they just pay back the material itself. So they basically have a free cladding for the building. This is the idea. And then you can see when you arrive at 100%, you start to have a very interesting internal rate of return. So if you have 100%, it means that the people in the microgrid, they don't have any benefit to buy your electricity. They could buy instead from the grid, but they also don't have anything to pay. So the price is the same. The person who invests is the local energy provider, so it's not them. So in this case, they can be green for no price at all. So me personally, I would do it. If they say, do you want 100% renewable electricity locally produced at the same price of your normal electricity, I would say, yes, why not? I'm a good person. Am I not? So next slide. So also this study, this is open access. It's published by MDPI, but unfortunately MDPI did an error with the charts, and I told them, and they uploaded the right version. Then I put the right version on ResearchGate, and then they re-upload the wrong one on MDPI. So that's why you can see the link is from ResearchGate. Please, if you want to read this article, read it on my ResearchGate page, because it's the official document that they published. There is also the logo of MDPI. That's the paper, but then they re-upload it wrong, and I couldn't fix this problem. So if you want to read it, please come on my ResearchGate page and watch it from here. Next slide, please. So finally, we arrive at the local energy market, which is the most complex, as we saw before. Next slide. Here we simulated a little bit better the houses, because in the first study it was a little bit random. So we also put a person that has the grow lights. Then we, of course, discovered that it can't be. So we simulate them more accurately with this load profile generator. Also, you can use this software. It's very interesting. Check also the paper of the guy, very interesting. Next slide. Yes. And here we have 6 scenarios. Basically, in this scenario 1, everybody buy PV and everybody sell the electricity at a very low price, but higher than the levelized cost of electricity. Scenario 2, everybody buy PV and everybody sell it at a high price, so 99% of the grid price. 3 and 4 are like 1 and 2, but only half of the people buy PV. This is very important because you will never be able to let everybody agree to pay some money. If you go in a large building and you say, okay, let's build a PV system, of course you will have 5, 6, 10 households who will say, no, I don't want to invest my money, I don't care, you can do it on your own. And so we made that case. So we said, what if in the local energy market 50% of the people don't want to buy the system? What happens? We will see. And then there are the 5 and the 6, where again everybody buy PV, but they have different strategies to set the price to sell the energy. Next slide, please. So we can see that with the new simulation, we don't have as strong as before the difference. Basically, we don't have the guy with the grow lights. So the largest households, the one with 5 components, are stopped just short of 8 megawatt hour. And we see that also in terms of self-sufficiency, it's a little bit more homogeneous, because we did some research on the actual people that are living in that community, and it's a very homogeneous community. So you can see that it's slightly higher, the self-sufficiency, so the people stay at home a little bit more than what we expected. This was pre-COVID, by the way. And still, it goes a little bit above, around 30, and especially the less self-sufficient houses are around 20%. But we see that, unfortunately, as before, the more you consume, the more you can get from the PV. The linear correlation is still there. Next slide. Then we can see the price of the electricity. Of course, some households have better self-sufficiency. Some households are better at using their own electricity, or at least the electricity from other households instead of the grid. And we can see that, of course, the price drops during the day. And we can see again that around 12:30, it's a bit more expensive than what it should be. You can see that little hump, and it's because the demand is higher, so you still have to buy something from outside. At night is 1.5 because it's the average between 1.2 and 1.8. Of course, at night, there is no seasonal difference between the electricity. Next slide, please. So here we can see the revenues and the saving. All the axes are in kilo coronas per year. You can see that, for example, the difference between the case 1 and the case 2. You can see that in the case 2, the electricity is more expensive, and so it's like a line. So the less you have as a saving, the more you have as a revenue, because it's basically the same. There are still some differences left. It's a bit complicated. We don't have much time. I would love to enter into detail if somebody is interested. You can see instead that the case number 1, there are some stronger differences, and especially the houses that are consuming more. You cannot see the legend because they are the subtitles, but those blue at 1400 kilosec savings, those are the very large household with 5 people inside. You can see that they have a higher saving compared to the other. Why? Of course, in terms of self-sufficiency, they are the same. But of course, the electricity that they buy from other households is cheaper, so they have larger gain. Then we can see the 3 and the 4 basically are similar to 1 and 2, but you can see that in the bottom left corner, there are some groups of households. In truth, I tell you, those are those who didn't want to buy the PV system. So of course, they don't have revenues because they don't own the system. But if the electricity is cheap, so in the case 3, they can have a little bit of savings, much less than the other because they only consume the excess electricity. So you can see also that if you do buy your share of the PV system, both your savings and your revenues are much, much higher than what they are if everybody. So if you have a larger share, your earnings are higher. This is also an interesting phenomenon. I'm writing right now this paper. I would love again to go into detail, but it's not possible. Then we see the case 5 and the case 6. Here we have different strategy. In the case 5, part of the household sell at a high price and part at a low price. The one with the red X are the low price sellers, so-called cheap sellers, again below the subtitles. So you can see that the cheap sellers in general earn more. So if you take every saving level, the cheap sellers are on the right. So it means that they are making more money. Why? Because they are outselling the expensive seller. So they sell for cheap, so they always sell. They have a self-consumption of 1. They can sell all their electricity, while the other, it's true that they can sell at a higher price, but really often they have to sell to the grid because nobody's buying their electricity. And then you have in the case 6, it's a very simple strategy, a very simple dynamic pricing, but in this paper we call them smart seller because they have a little bit of intelligence. So basically they look the hour of the day and their consumption, and if they have an outlier high balance, so if they have too much electricity, they assume that everybody has electricity, and so they decide to sell at levelized cost of electricity. This strategy is very simple, and it's also very flawed because it could be that you have a lot of electricity in that hour, but is not common. Maybe the electricity is scarce, so you are selling it for cheap in a moment in which you could sell it for expensive, and the other way around. Maybe you have a outlier low consumption in a specific hour. So it's actually a stupid strategy. It's not well designed, but it was just like the first trial that I made. And of course, it was super effective. So you have the cheap sellers against the smart seller, and the smart sellers are winning hands down, you know. Even though they are not smart, they could be way smarter, but this is just an indication that if there will be energy markets in the future, there is obviously a strong need for selling for price scheme, you know, dynamic and clever price scheme. It's like a service sector. Next slide. This slide, it's like the previous, but in this case, we see the internal rates of return. And this is a very conservative internal rate of return because we assume that the electricity is not growing. So the price of the electricity outside is not growing. This is considered conservative in the PV community, at least. So the internal rate of return could be much higher. But you can see that, of course, in the case 1, when the price of the selling is low, there is a strong difference. So you have the people who consume more that have a much higher internal rate of return. While in the case 2, where where the prices are high, basically it's much more balanced. Of course, you still have this aspect because the large consumer have usually higher quantity of energy from their own PV system without even thinking about selling. So already from their own, they can consume more. And therefore, they have a little bit more benefit, but the whole thing is more balanced, as we saw before. So then we have the 3 and the 4, which are very similar to the 1 and the 2, but you can notice is noticeably higher. So everybody is earning more. Why? Because you have a larger system, so your self-sufficiency go up. And then when you are overproducing, there are plenty of people who do not have a PV system. So you can basically, by being a shareholder, by having a larger share of the same system, your internal rate of return are higher. So even though you invest more, you will get so much more than the internal rate of return is higher. So this is a good news, because if you go in a large building and you say, okay, let's build the PV system, and you see that many people disagree, so they don't want to finance, this is a good news for the others. This is a good news for those who want to finance. And this is a very, very positive result from this study. Then you can see the case 5 and the case 6 again. And you can see that in the case 5, the cheap sellers tend to have a higher internal rate of return. And in the case 6, the smart sellers, of course, as we see, they outcompete completely. So invariably, they are always on the right side of the chart, while the cheap sellers, the former cheap sellers, those who sell at 1 corona, those are invariably left on the left, so on the lower internal rate of returns. Next slide. So we have the key takeaways, but I'm sure you understood, and I really need to leave some time for the questions. And if you want, next slide, please. If you want to contact me, please visit my ResearchGate and send me a message there. I always reply from there, much better than the email. Thank you everyone.
Okay. But thank you, Marco, for this very interesting speech, very technical.
Yeah, sorry.
No, it's good because we have different competencies in our room, so they are aware that this possibility to have some speech more general, more theoretical, more technical, so it's obvious. Maybe we have some question. No, just to thank you for your speech from the participant in the chat. And I thank you again for your participation. And I invite you, as already before with other speaker, in our laboratory to help our participant to develop the project. So if you like, you are welcome to join us during the lab, and see you soon. So
thank you a lot. I would love to stay, but as you know, I'm quite east of you, so it's definitely time to go sleep for me. But thank you very much for the attention, and I hope, I apologize if it was too technical. I hope I could inspire somebody in the audience.
It was very interesting, all the typology of energy communities you show us. So I think it was very inspiring for the participants. Thank you again.
Thank you a lot. Bye-bye.
Bye, Marco. So